to go negative, and normal forces can't be negative. So at the point where it's 0, it'll leave the surface that's exerting the normal force, or the two surfaces will lose contact when the normal force tries to go to 0. The other thing would be if an tension tries to go negative. That means your rope or cable or what have you will go slack, but there's no rope or cable here, so that obviously it's going to be the normal force. So what I'm going to do here is we're going to have to look at the normal force here between the block and the sphere and see when that normal force gets to be 0. So that's going to be part of the problem. So we're going to do an FBD of the block while it's sliding. Okay, so say it's right here at, a position theta. What you have is of course, the block's weight acting on it, as always, and then you have the normal force, which acts at an angle theta off of vertical. Okay, so in order to analyze this, what we want to do, I think, is look at axes like this. So an axis parallel to the block surface, which is x, and an axis perpendicular, x, there we go, and an axis perpendicular, which is y. So here we go with x and y is, of course, at an angle theta off of vertical. So let's see, to break this down, sum of forces equals ma. And what I'm doing here is I'm just taking the FBD as far as I need to get the components out and solve for what the normal force is going to be. So normal force going that way, and then gravity gets broken down. Now this angle here, these are opposite angles, so this is going to be theta, which means then gravity gets broken down into a component that goes along the surface of the sphere, which is going to be mg sine theta, and then a component that goes perpendicular to the surface of the sphere, which is going to be mg cosine theta. Okay, so now the forces this way are going to add up to sum of forces in the y direction are going to be your normal force going the positive y direction, and you're going to have that component of gravity going that way, and those are going to add up to m times your y acceleration. Now you're also going to have acceleration in the x direction. I'm not going to deal with that, but the acceleration in the in the x direction, in fact, is what makes the block go faster or slower. The y direction acceleration is going to be your centripetal acceleration. So at any point where the block is, it's going to accelerate towards the center. It's got this acceleration that's centripetal, and it's also going to have, if it's off the center, it's also going to have some what we call tangential acceleration, which is acceleration along the surface of the sphere that causes it to go faster. So there's two components to the acceleration there. What we're interested in here is the centripetal, because that's the one going along the axis where the normal force acts, right? So when you're at, say, this position here, your y-axis points away from the center of the sphere, and your centripetal acceleration is pointing towards it. So the situation here is that ay is equal to the negative of your centripetal acceleration. Okay, so I've said before, the fundamental equation you use for centripetal circular motion problems is A equals A, and this is true, but it's not always one A equals another A. You have to set them equal the right way, and in this case, it means the y component of acceleration that we get out of our free body diagram has to equal the centripetal acceleration, but the negative of it, because the centripetal acceleration goes in the negative y direction. For example, when you're right there, that's the way you're accelerating. So negative centripetal acceleration. So easy thing to do, of course, here is to multiply both sides by m equals negative mac, because then you can just plug in this expression here for your may. So what I'm going to get here is normal force minus mg cos theta on the left-hand side is going to equal negative m, and then your centripetal acceleration, we're going to use v squared over r, where r is the radius of the sphere. So this here is r. We're sort of assuming, by the way, that the radius of the sphere and the mass of the block and even gravity are going to, we're going to have to use those in the answer. We're hoping they'll cancel out. We're okay if gravity doesn't cancel out, because we're sort of assuming that, that's always a given. but we weren't given the mass of the little block, and we weren't given the radius of the big block of the sphere as part of our given. So we're hoping that those things will cancel out, right? So at this point, this is sort of what we get for the first part of the problem. Actually, I guess, well, I probably shouldn't have boxed that. So, undo, nice. What I'm going to do is solve that from the normal force, because we want to find the point where the normal force goes to 0, right? That's what we were talking about. When the normal force goes to 0, the block leaves and flies off. So normal force is going to be m, and then what I'm going to do is, since I moved this part over to the left, I'm going to say it's m, well, I'll just say it's mg cosine theta plus mv squared over r. Sorry, that's a little cramped. So let me make it a little nicer in the next step, which is going to be Fn equals m times g cosine theta plus v squared over r. Okay, so that gives us something there. Okay, now what I want to do is find out, because v varies as you accelerate, right? Or as you start, as it slides. So up here at the beginning, you have v equal to 0, and then v increases, 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 okay? So the fastest way to find out what v is going to be at any given point is to do an energy balance. In fact, in this case, really, that's the only easy way. You can do this, I mean, if you can do kinematics, 2D kinematics, well, not 2D kinematics. If you can do, well, I mean, you have to integrate to do with kinematics, basically, I guess is the point. So anyway, but we're using energy, and the nice thing about energy is that it saves you from having to do calculus. So this is a case where the only force is acting. Since it's a smooth sphere, we have no friction. The only force is the normal force. And the normal force is going to do 0 work because your path is always perpendicular to the normal force. That's the case. That's pretty much generally the case when you're sliding along a surface and the surface is not flexing or moving under the thing that's sliding over it. So this is going to do no work. And then the only work done is going to be work done by gravity. And we could go through the whole thing where we say network is change in kinetic energy, and then network is work done by the normal force plus work done by gravity. Okay. Oh, look, I am doing the whole thing. Okay, fine. Work done by normal force we said was 0, and then work done by gravity is negative change in potential energy for gravity. Okay, equals delta K. And what that comes out to is delta K plus delta UG equals 0, or mechanical energy is conserved, which is K plus U. So what I'm going to do then is find, I'm going to say this is my position 1, and then position 2 is, we'll say, some later time. Okay, so 1 is the start and 2 is a later time. 1, we have potential energy due to gravity equal to mg times the height of the block above whatever reference point we choose. I'm going to choose the center of the sphere as the reference point because I know that this works. Okay, and it doesn't really matter. Okay, but what's nice is then you can say that the well, I'll show you in a minute. So its height above that is the radius of the sphere. Okay, and then its kinetic energy at that point is 0. Okay, at point 2, the potential energy for gravity is mg, and then how high up are you? Well, you're up this high, and that distance is, or it's, this here, right? Which is r, the radius of the sphere, times the cosine of the angle theta. So mg r cos theta, and then k is 1/2 mv squared. Okay, so now you set, k1 plus u1 equals k2 plus u2 because you have no non-conservative forces here. And what you're going to get is mgr. Wow, what the hell was that? Okay, mgr equals, and you have no kinetic energy at the beginning, so it's 0. On the right-hand side, you're going to have mgr cos theta plus 1/2 mv squared. And so when you, let's see, what happens then? You get, I'm going to multiply everything by 2 over m because I want to solve for v squared, okay? So what I'm going to do, I get 2 over m, and I get 2gr Actually, I'm sorry. I'm just going to solve for the kinetic energy first. So I'm sorry. 1/2 mv squared equals mg r. Okay, that's this term here, and this flipping the signs, and then this gets subtracted and moves over there, but then it comes over to the right-hand side because I flip signs, and that's going to be mgr times 1 minus cosine theta is your entire right-hand side. Okay, so then what you'll get is that v squared, now I'm multiplying by 2 over m. Okay, hold on. There's my equal sign. So multiply this by 2 over m, you get v squared equals 2gr times 1 minus cosine theta. And now what you can see here is, okay, so this is what we're going to use here. And then we also have this. Okay, so we combine these two. So combine these two now and setting the normal force equal to 0. Why don't I... So what can I do? Well, I'm just going to try to cram it in here. So, actually, no, I'm not. I'm going to just erase a bunch of crap in here. And let's see. There we go. Close enough. Oops. Okay, so going from these two now, what I can do is I can take this v squared here and plug it in up here. And in fact, I can turn this thing into v squared over r, okay, is equal to 2g times 1 minus cosine theta. And now this whole thing is this whole thing. So I can just plug this guy straight in there. And what I'm going to get is normal force equals m times g cosine theta plus 2g, and I'm just going to go 2g minus 2g cosine theta. Pardon me for sort of, doing some of the algebra a little too fast, but I don't think this is good because it shouldn't come out like this. It should be... So what did I do wrong? I bet and I probably erased it now. The normal force is... Okay, so you know what? This should be a negative... Oh, sorry. This in here should be a negative sign. I'll bet you anything. So let me see if I know how to use an eraser here. And I pretty much guarantee I don't. Okay, whoa, that's too big, but... Yeah, well, there we go. Okay, so... No, wait, no, it's not. Oh. Wow, it's like a soft eraser that sort of slowly fades things out. Like a crappy eraser that... Okay. Well, there you go. Okay. It's nice that in our digital age, we can now simulate crappy things. Okay, so I'm just going to change this now to a minus sign. Now it looks like a dot for dot. Oh, jeez. There we go. Okay, and now I'll just get rid of that. Fine. Someday I'll actually, see, my problem is I never sit down and try to learn this program before I start doing video. And I really should just do that. Anyway, so there we go. That's what we should have had. And then when you do the subtraction, this becomes negative. Okay, screw that. I am just making that negative. So this does not look like any symbol. This is not a dot. This is like an electric guitar, okay? And there's no electric guitar operator, so that won't confuse you. Okay, so then